Okay, all right. Good afternoon, everyone. This is Celso Batalha, Evergreen Valley College, and this is Astro 10. And today I would like to, before I go over some of the subjects we discussed this week, which is about the moon and the interaction between moon and Earth, a few students are asking for the seeds in future discussions, and let me show you quickly where or when these seeds will occur. And to do that, I need to share my window. So if you go to our course in modules, and my connection is okay. Then it's the module 1, chapter 1 is done, and then we have a chat room uploaded there, which I did on Wednesday. Last week chat room is here, and today's chat I'm gonna upload and put it right here. But see, the discussion, if Earth is a sphere, you don't need to collect any seeds today. It's just a matter of studying the book itself and write your opinion. Now, next week we have Astro News. And then Astro News, if we go there, there is an article we are supposed to read, and then you have to write a report. So this report shouldn't be extensive, as I mentioned in the syllabus, but you have to write in few lines what this paper is all about, right? And how, I mean, usually when a group of scientists accomplish something, they have a goals, and that's what you write in the first 4 lines or so of your report. And the second one, you have to describe how did they accomplish that. I mean, how did they get those goals done, basically. And then the third one is a seed. So this seed, you have to attend the chat room, or you have to watch the archives of that particular chat room, which is going to be next week. But next week on Monday is a holiday, so I'm going to do this on Saturday. So this Saturday, I will, at noon, I will open the chat room at noon, Saturday noon. So if you were there, that's great. I will announce that to the class so that you can start preparing your report a little earlier if you want. But these seeds will be delivered on the day of the chat room. It's a way that I have to make sure the students are kind of following or contact me and get information and all of that. Okay. So this is the first issue that came about a few times this week with some students. Now, this week we are pretty much in the system Earth Moon. Let me show you one thing. Can you see this? Let me now stop sharing. There you go. So this is a model, of course. Let me go further. This is a model of Sun, something which I don't know what it is. Could be Mercury, could be Venus. I have no idea. And here's planet Earth. Now this white ball represents the moon. Now, this system is not in scale, by the way. The Sun is not that size in respect to Earth. The Sun is, in fact, 100 times as big as Earth is. The ratio between Earth size and Moon size is 1:4. So Earth is 4 times as big as the Moon. But the Moon is not that close from Earth. So how would we place the Moon? We would take basically Earth diameter, this sphere over here, and take 30 of them, one next to the other, 30. 30 Earth. And then at the end of this string of 30 Earths, you would place the moon. Okay. So when we study moon's phase, this is the phase we call new, and this is the phase we call full, when the moon is further out. In my model over here, the moon is an eclipse. So eclipses don't happen always, because now think about it. You take this Earth, put 30 Earths one next to the other. In my room, I would have to place the moon pretty much on the wall over there, and the chances of having this moon falling on Earth shadows are pretty low. So it happens every 5 months or so when this might occur, and only on those periods is that eclipses occur. Now, moon goes every month through the new and full phases, right? Moon, if I can allow the system to go, look at that. Oh my goodness. The moon is looking from a north celestial pole configuration. So all this system seems to be going in a counterclockwise direction. So that's how we go. So counterclockwise direction for me and for you guys, which you are looking north, that is not correct. So Earth goes looking north, so Earth is going in a counterclockwise direction. So I should have done this way for you guys. Sorry about that. So that's how it goes. And my laser point might start falling here. So this rotation, the sun is in the center, and you have all this nice display going on. And I'm looking from the southern perspective. For me, it's a little bit different, but that's how it goes, right? So the sun, if you are now on Earth, you don't perceive this motion at all. So on Earth, instead of having these things happening like this, what we really see is this situation. So Earth is immovable, and then, oops, the sun is the one going around Earth. It's kind of difficult to move this, but that's the idea. Another point that I want to show in the simulation is I have a laser pointer. So if you can see this dot on Earth right here. So this is where the sun is shining on Earth on some particular time of the day. But take a look at the orientation of Earth's axis of rotation. So when Earth goes about the sun, and I'm doing such a way that I'm trying to keep 3 things here organized, and it's not going well. No, I'm not going to use this simulation. My laser is not steady. Try again. See that dot is pretty much close to the equator now? We call this moment equinox. Let's see. Yeah, it's not steady. I'm not going to do that. I'm going to use a simulator better than this model. Sorry about that. Let me.
Okay, this is
All right, so let me use a software instead of my model that's not working now. But here's the moon's phase simulator, which explain the following issue. Of course, we go out and we see the moon goes through phases. So what is causing these phases? You gotta include in the mix, in order to explain moon's phase, three components. The first component is the sun itself. In our solar system, the sun is the only object capable of producing optical light. Everybody else reflects that light, in some way reflects that light. The moon does reflect light, Earth does reflect light. And before I start the simulation, if you look at the moon, which is right here, I hope you all can see my window, and Earth is right here, and we, as an observer in the simulation, we happen to be in the north celestial pole looking down on Earth. So Earth, as I mentioned, rotates and orbits the sun, as seen by somebody standing north, in a counterclockwise direction, which means Earth goes around itself like this. Now, as Earth rotates on its axis of rotation, look what happened in this window down here. Can you all see that? So as you look in the window, let me put these little people right at the sunrise. See that? Sunrise over there. So for that person now looks east and see the sun pretty much rising. Now, when this person happened to be at this location, is the local noon for that person. Time to get a sandwich. And then Earth rotates another 6 hours, and that person looks west and then see the sun setting. Now, as Earth rotates, take a look at the moon's phase. The moon's phase is not changing at all. That gives our first point, and that is moon's phase has nothing to do with Earth rotation. So Earth rotation is not an issue here, right? Also, Earth orbit around the sun is not an issue. You could have Earth going around the sun, keeping the moon system going on the way it is, and the phases wouldn't be affected. Even if you stop Earth from going around the sun, the moon's phase wouldn't be affected, as long as everything else remain the same way as it is now. Now let's take a look at the moon itself. The moon orbits Earth in a counterclockwise direction, as seen by somebody standing north. Now look at the moon's phase there. Now we go through a quarter phase, first quarter, and then we go to a full phase, and then we pass through the gibbous waning phase to a last quarter, and then finally we go to the crescent waning phase back to the new moon. So the moon's phases occur because of the relative position of the moon, the sun, as the moon orbits Earth, basically. And as you can see, at any given, and I will start animation, at any given position of the moon's orbit around Earth, both the moon and Earth are always 50% lit by the sun, because they don't have proper light. So Earth is on the left-hand side, as well as the moon on the left-hand side, completely lit by the sun. So the phases, the moon phases, are the result of us observing and seeing some percentage of that lit hemisphere. So when we see nothing or none of that lit hemisphere, we call moon phase, and this is pretty much here. So see, the hemisphere is lit, but we don't see any of it. Whereas in the full phase, we see the entire lit hemisphere. And in the other intermediate phase, we see some of it, basically. Okay. Does that make sense?
Yeah.
Okay. Now, the question now is, okay, how do we figure at what time of the day certain moon phases are supposed to rise and set? For instance, let's first of all forget about the moon and let's think about hour of the day. So if you have a system like the sun on the left-hand side, Earth, and a little person that is standing at the equator, like in this figure. So since Earth rotates counterclockwise as seen by somebody north, this is the rising moment or rising time, so 6 a.m. And 6 hours later, because of Earth rotation, this person's going to be sitting at this location, and this is noon. So the sun is crossing the meridian of that person. And then 6 hours later, at 6 p.m., this person is going to be here. So you should be able, when you try to figure at what time of the day certain moon phases are supposed to rise or set, you should be able to design and to sketch this clock. 6 p.m., midnight, 6 a.m., noon. Well, let me see if we can do that in a blank piece of paper. Let me give my annotating. So the first thing first, we need the sun. So this is not complicated, just bring a sun. And then you bring Earth. North Pole. You all see that? So then we know Earth rotates like this, following this arrow. So when the sun is high up in the sky, for somebody standing here, the time of the day is noon. Because Earth rotates counterclockwise, as seen by somebody standing north, at 6 p.m. this person should be here. This is 6 p.m. Since Earth has an entire cycle of 24 hours rotating, when Earth moves another 6 hours, this person should be here, and this is midnight. And then 6 a.m. is right here. So if you look east, you see the sunrise. If you look west, you see a dark sky. In fact, darker than looking east. Now, if you're here, you look east, and you see a rising star. You look west, and then you see the sun setting. The sun is setting. Okay. So stars, the sun, the planets, they rise in the eastern sky. Like here, the sun is rising in the eastern sky at 6 a.m. and they set, stars, planets, and the sun, they set in the western sky. As a review, let's remember Starry Night software that I showed last week. If we get rid of daylight, is the sun in the sky. Let's just bring the ecliptic line. It's always good to have the ecliptic line. And if we allow, and let me also bring labels of planets and moons. There you go. And if we allow the time goes by, see the time is changing, 1:28, 1:40, 2 o'clock, 2 p.m. So the sun sets in the western sky. This is the western sky. The planets also set in the western sky. Venus is going to be setting. And if you look east, then you have rising situations. So stars, the planets, and the sun, they all rise in the eastern sky. They all set in the western sky. And this is the result of Earth's rotation on its axis of rotation. So then is the clock. So now let's position the moon in this clock. So you should be able to know that the new phase is a phase where the moon lies between Earth and the sun. So this should be a new phase. In the new phase, none of the lead hemisphere, if this is the lead hemisphere, none of the lead hemisphere is seen by anyone on Earth, because all the light is being reflected everywhere except towards Earth, right? None of the reflected moonlight. By the way, there is a movie, Moonlight, which you guys should see. It's fantastic. So none of the moonlight reflects back to Earth. Now also, you could not see the moon in the sky, even if the moon had some intrinsic brightness, because the sun is too bright. When the moon is in the new phase, the moon happens to be pretty much close to the sun. Let's take, for instance, the software and try to visualize that. Let me stop here and change for days. See the moon right there? So the moon, let me expand this a little bit. In the new phase, if we bring this daylight back, this is it, right? The moon is in the new phase. See, the moon is over here, a little bit to the left. The sun is more to the right. And there was a moon eclipse. The last full moon, the moon was an eclipse. We couldn't see much of it. But that goes to show that the angular size of these two bodies in the space are basically equal to one another, half a degree. And so when the moon happened to be in between the sun and us, we call that eclipse. But eclipses are rare. It doesn't happen all the time. And that was one of the reasons why ancient Greek philosophers, they indicated, they suspected, and they proposed that the sun is further out in respect to the moon, because the moon would cover the sun. So the moon has to be in between us and the sun. So the new moon happened when it is in perfect alignment with Earth. And I try to go back here on time. There you go. See, that should be almost the new moon. Let me see. Yeah, discolluminated 2%. So it's pretty much close to the new moon, right? So and it's not blocking the sun at all. But the main point is, even if you could see any of the moon, the sun is too bright. The new moon happened to be in a sky position that is pretty much close to where the sun is. So, and then we don't see the new moon. But 7 days later, as the moon keeps orbiting Earth in its counterclockwise direction, so 7 days later, the moon is going to be positioning right here. And we call this phase first quarter. First quarter. So it's first quarter because if we are on Earth, we can see half of the, so if we are anywhere in a good position on Earth right here, we can see this much of the moon, and then half of it is bright, the other half is not. So, which means we see a quarter of the entire moon surface bright, and that's why it's called the first quarter. The second quarter is the so-called full moon. And then we see 2 quarters nicely lit, and that is equivalent to a half hemisphere bright, and that is the so-called full moon. Now, the phases between new and quarter are called crescent phases. Crescent phases. And the phases between quarter and full are called gibbous phases. Gibbous phases. And the moon kept orbiting Earth, and then about 21 days or so after the new phase, the moon goes in its last quarter, last or third quarter. And finally, it is in the new phase again. So these phases from new to full are called waxing phases. Waxing phases. And the phases from full to new are called waning phases. Waning phases. Now, new moon, first quarter, in fact, crescent, first quarter, and then gibbous phase. This part is kind of a fuzzy, and this is nicely sharp. It's more than 50% lit. So crescent. Crescent. This is first quarter. Gibbous. Gibbous. And then it goes to the full. And then when it goes to the waning gibbous, the sharp edge of the moon is to the left-hand side. And this is the fuzzy part. Because in the sky, the sun is to the left, is eastern of the moon. And then it goes to the last quarter, or third quarter. And then it goes to the crescent phase. So the waning phase, they happen to have a phase, a shape that is contrary, that is reverse from the waxing phase. So this is reverse to that, these reverse that. So those are the phases. You have any question, or is all right?
Yeah, so fine.
Okay. Now, the last thing I would like to show is, okay, how do you find at what time of the day a particular moon phase is supposed to rise or set? So there is a little trick. Let me show you how you can figure that. There you go. So you start, let's say you have a moon that is waning crescent. It's a waning crescent. By the way, the waxing crescent, I'm sorry. The waxing phase, the sharp part of the moon is always to the right because the sun happened to be to the right. In the waning phase, the sharp edge of the moon is to the left. And why? Because the sun is to the left. Okay. So the sun shine on these edges and make them sharp. You can, with a telescope, you can see these sharp edges quite well, and the one to the right in the waning phase, they are kind of a fuzzy. Let me see if the Starry Night can show me that. Today, if we go today, the moon is in a waxing. Let's go to, there you go. So 12 a.m. that's the moon in a phase that is called waning gibbous. Gibbous because more of the half of what we see of the moon is bright. Now, what is waning? If you look at the moon, even in the software, the left-hand side is sharper than the right-hand side. You see that? We can even perhaps center. And magnify. So the left-hand side is sharp, the right-hand side is fuzzy. So the terminator, it's called terminator, you can't see well in detail. Why this edge is sharp? Because the sun is to the left, the sun is east. And that's the characteristics of waning phase. In the waxing phase, if I look at the moon 14 days from now, so 14 days would be 27, right? February 27. That's then the sun is going to rise and increase this. The sunrise. Oh, I think I got. Stop there. Let's go 28. All right. So here's a waxing phase, and let's center on the moon. And let's magnify. Past the clouds. And that's the moon. So I'm going to get rid of daylight. Now, in this phase, in the waxing phase, the sharp edge of the moon is to the right, because the moon is west, the sun is west of the moon, and the terminator is right here. So waxing phase is, as you see the moon in the sky, the right-hand side of it is nicely defined. And in a waning phase, the left-hand side is nicely defined. Now let's pick one phase, and this is the so-called is a waxing crescent. So we want to answer the question: at what time of the day this moon rises and sets in the sky, right? So how do we do this? We start placing the sun. That is required. And then we place Earth somewhere. And then we know that since we set the sun here, since we set Earth here, we know in a clock this is noon. This is 6 a.m. This is 6 p.m. And this is midnight. Why do we know that? Well, because noon is because the sun is high up in the sky. Earth rotates counterclockwise. So a person sitting right here, 6 p.m. is going to be there. Midnight is going to be here. 6 a.m. is going to be there. Now you need to know, to find out what time this waxing crescent moon is supposed to rise and set, you should be able to put that moon in this diagram. How do we do that? Well, we know the new moon is here. The new moon is in between the sun and earth. So where should the full moon be? Further out. And the quarters are here. This is first quarter, and this is last quarter. Crescent phases are in between the sun and the quarters phase, new and quarter, and the gibbous between the quarters and full. So a waxing crescent phase, the moon should be somewhere here. This is a crescent and is a waxing phase. So the next thing you know, that's the tricky. You take a line from the moon to earth and do a little T, like a T letter. So a line connecting center of the moon, center of earth, draw a T. And here is your setting time. Setting time. And here is your rising time. Rising time. The next thing you need to know is to read the clock. So the rising time is somewhere around 9 a.m. The setting time is around 9 p.m. roughly speaking. Okay? So let's try another one. Let's try a gibbous moon. So a gibbous waning moon. Waning moon, gibbous, sharp edge to the left, and then you have a fuzzy, that's the moon. Let me erase all of this. Should find a more efficient way to do that. There you go. So I don't want that. Take the setting time away. So this is much better than try to memorize a battalion of things, you know. You do the diagram. I mean, after you do a few times, you should be able to do yourself. So let's do it together here. So we start with the sun. You have the sun there. And then we want to place Earth. There, what it is. So we have the sun, and then you have Earth. Next thing you do is to place times, right? So here is noon. And then since Earth goes counterclockwise, 6 hours later, this is pretty much 6 p.m. And then another 6 hours, we are midnight. And then another 6 hours, we are 6 a.m. Now, because the rotation goes counterclockwise, and since we know this is our new phase, that's where all start. The moon in a new phase lies between Earth and the sun. Then we know after the new we have the waxing phases up to full. Those are waxing phase. Looks like a happy phase, waxing phase. And then we go to the waning phases. Those are the waning phases. Since the moon that I want to find at what time is supposed to rise and set is a waning gibbous. So where should I place this waning gibbous moon? Well, waning should be in this part of the diagram. Gibbous should be somewhere here. What I do next? Connect a line from the moon to Earth and make a T. And then I find my setting time. And then I find my rising time. So what rising time this is? 9 p.m. I have to read the clock here. And this is at 9 a.m. So how do you know if it's rising or set? Well, if I'm sitting right here with a pair of binoculars, a few hours later, I still can see that moon in the sky because Earth rotates like this. I still can see it. But if I'm sitting right here with a pair of binoculars, a few hours later, I'm going to be sitting right here, which means I can't see the moon anymore. So the moon at this position is setting for me. Now this is the most kind of a technical, complicated material that goes on moon's phases. Is to figure out at what time the moon is supposed to rise and set. But if you follow this trick, you should be able to do it all right. You should be able to. All right.
Okay.
All right. Also, in this diagram, in this chapter, tidal forces are explained as the result of gravity forces, and gravity forces chapter 3 and yes, so it would be nice if you know what gravity is. But you have experience of tide, and tides occur because Earth and Moon have an attraction. It's called gravity, and the Earth water bulges out towards the moon, kind of rises up because it's attracted by the moon itself. And the Earth itself is attracted too, and the least attraction goes to the water in the other side. So if you are looking from the space, you have Earth is slightly bulged on. In fact, what can be bulging is fluid, which means atmosphere and water, towards the moon and away from the moon right here. So as Earth rotates, you can see this bulging water to rise and set twice a day, basically. That's why twice a day we have rising tides and then low tides. This is high tides and low tides 6 hours later, in kind of about 6 hours interval. In other words, if you are going to Santa Cruz and you want to see, you're going to play in the cliffs and find tide poles and play with animals, little crabs, and take kids there. So you are an astronomer, so when is the best time to go? So you want to go there when the tides are low, which means you should look around and see if you can spy the moon in the sky. If the moon is closer to horizon, that's good. Because the moon being closer to horizon means you are, oops, I can write it again. So here's Earth, here's the bulging water, and I'm not an artist. I was not born with that skills. And the moon is somewhere here. So we have an attraction between those two bodies. So if you happen to be at this location, that's great. You see the moon in your horizon. This is low tide. This is low tide. And this is high tide. Right, so you wanna be here. So every 6 hours or so, Earth goes through this process of high tides and and low tides. Now, in fact, because of rotation, this bulging water moves a little bit in the direction of Earth rotation, so it's not exactly underneath the moon. The moon is a little bit off with respect to the bulging, so it's kind of like this, as a few degrees with respect to that, kind of a few 4 or 5 degrees or so. All right, and the tides are the biggest when you have a nice, it's called spring tides, when you have almost a perfect alignment between sun, earth, and the moon, because now both the sun and the moon exert a pulling force on earth water, and then you have the high tides, the highest possible, called spring tides. But when the moon is in a quarter phase, like if the moon is in a quarter phase, the high tides are not the highest possible. They are called neap tides, and that's because you have some the combining forces of the moon and earth on earth water is the least possible. So other than that, pretty much that's it. I will email the class probably on Friday and let you guys know that on Saturday I might be doing the chat a little earlier. If I cannot do on Saturday because it's holiday, people might be traveling, I might push everything, all the talks to Tuesday, but I will see, or perhaps a little earlier. Okay?
Okay.
All right, Thor, as always, thanks for coming. It makes this chat room, at least for me, not so much empty.
Right.
Yeah.
My screen froze. That's why I disappeared for a minute. I had to reboot my computer.
Oh, is that right? Oh, geez. Yeah, mine is sometimes does something like that, especially when my computer gets full of videos and then I have to start deleting things. All right, man.
Okay. Take care.
Take it easy.